G'day, Group 15 here. I'm just going to read through problem 4. Problem 4 is a logistic population model. A nonlinear first-order model for population growth is a logistic population model given by dp over dt equals r in brackets 1 take p over k in brackets p, where pt is the size of the population at time t in brackets in years. R is the reproduction rate of the population and k is the carrying capacity of the environment. Assume that you have the following measurements. Year 1990 where the population is 100, the year 2000 where the population is 130, the year 2010 where the population is 160. These are initial values used throughout the solution. Now we have to solve the differential equation and determine R and K. From this, predict the population size in 2020. Fractional animals are perfectly fine. Can you comment on the population size in the long run as T becomes really large?
Alright, good morning. Welcome. This is Group 15's answer to problem 4 on logistic growth models. And this is for the 106 peer review 2018. So originally we were given this equation for dp over dt. And we wanted to get p by itself in an equation. So we took 1 minus 1 over kp to the other side to get r dt by itself. We then needed to integrate each side. On the right hand side that gave us rt plus c. But on the left side we times each side by k over k to get this equation, k over bracket k minus p and bracket p. And then we use partial fractions decomposition to get 1 over p plus 1 over k minus p. We then integrated that to get ln p minus ln k minus p equals rt plus c. So then, using log laws, we rearranged this equation to get ln k minus p over p equals minus rt minus c. And then we expedited both sides. We've got ln k minus p over p equals minus rt minus c. And then we got to here, which is k minus p over p equals a times e to the power of negative rt, where we let a equal e to the power of negative c. Finally, we took p over the other side, we got k minus p equals p times a times e to the power of negative rt. In conclusion, we rearranged the equation once again to get p by itself, and we got the equation p equals k over 1 plus a times e to the power of negative rt.
We now find an equation for k, which is equation 1, with p now found. We sub p naught equals 100 and the function p0 equals 100 into equation star, which leaves us with 100 equals k over 1 plus a. We rearrange the denominator to isolate k, which equals 100 plus 100a equals k. This is equation 1. We sub equation 1 into star to find in terms of p. We sub 1 into star, which gives p equals 100 plus 100a over 1 plus ae to the power of negative rt, which is equation 2. We substitute the two given values into 2 to find in terms of p. We create new equations 3 and 4 using the initial values. We sub in the function p10 equals 130 and the function p20 equals 160 into 2. This leaves us with 130 equals 100 plus 100a over 1 plus ae to the power of negative 10r and 160 over 100 plus 100a over 1 plus ae to the power of negative 20r. We rearrange equation 3 to find a in terms of r. We have 130 equals 100 plus 100a over 1 plus ae negative 10r. We rearrange the denominator to get 130 plus 130ae power of negative 10r equals 100 plus 100a, which leaves us with 30 equals 100a take 130a equal ae to the power of negative 10r. We rearrange for r, which equals which a equals 30 over 100 take 130e to the power of negative 10r. We sub 5 into 4 to find r, which leaves us with the equation for 160 in terms of only r and e. We compute r and determine the valid solution. We plug into equation solver using graphics calculator to find r, which leaves us with this equation. The valid solution for r equals 1 over 10 natural log 8 over 5.
After computing the value of r, we can now find the values of a and k. Substituting the value of r into equation 5 to find the value of a. When a is equal to 30 divided by 100 minus 130 multiplied by e to the power of negative 10 multiplied by 1 on 10 log of 8 on 5. Therefore computing a equal to 8 on 5. We can now substitute the value of A into equation 1 to find K, such that K is equal to 100 plus 100 multiplied by A. This is given as equation 1. Therefore, we compute K is equal to 260. We come to the conclusion now that our implicit solution to the first order non-linear growth model is found by P is equal to 260 divided by 1 plus 8/5 multiplied by E to the power of negative 110 log on 8/5 multiplied by T.
After finding an implicit solution, we've used the Desmos online calculator to graph our result analytically. We can see here that our function of P equals 260 divided by 1 plus 8/5e to the power of negative 1/10 log of 8/5t goes through the y-intercept at 0, 100, which was the population at 1990, and then the 2 points after which is 10 years and 20 years, correspond to the values that were provided. Therefore, we can see through graphical analysis that our logistical growth model is a valid solution.
Given that this solution is now valid, we can now predict the population in 2020, which is the second half of the question in problem 4. We can do this by substituting t equals 30 into p of t, because it's 30 years past t of 0, which is 1990. Therefore, given that p is equal to 260 divided by 1 plus 8/5 multiplied by e to the power of negative 1/10 ln 8/5 multiplied by 30. Therefore, this gives P equal to 186.966. Thus, the population in 2020 will be 186.966 animals according to the logistic growth model.
We can graphically confirm our solution to the previous question through using Desmos. Here, we have plotted the straight line at x equals 30 onto the graph where our model was already plotted. You can see the intercept of the two lines at 30 and 186.966, which therefore means in 2020 the population will be 186.966 according to our model. The third and final part of problem 4 asks us to comment on the population size in the long term. For this we used Desmos and expanded the t-domain to 350. We also plotted the point 350 and 260. We can see through the graph that it seems to plateau at a certain point. Through our point we can see that this is 260. Therefore, in the long run, the population size, according to our logistic model, should max out at 260, or should I say limit at 260 and not become any bigger.